Hey everyone, my name's Arnav. I also go by Arnave online, and I'm here to present the TraveLog solution from the 2021 NAC. Really quickly going over the problem statement, Bob takes some shortest path from his home in City 1 to Alice's home in City N. He also has this device called a TraveLog, which records the distances from City 1 to every city on the path he takes. So running through the sample input really quickly, if Bob takes the top path, then his travel log will record 0, 3, 7, and 9, which are the distances to the vertices on the top path. If Bob takes the bottom path, his travel log will record 0, 5, and 9. However, Bob's really efficient. He takes shortest paths, but he's still kind of unlucky. His travel log gets corrupted. It's missing some data. The remaining data is scrambled in some order. Your task is to determine which path Bob took. It's also possible that there's no valid paths or there's many valid paths. If one of these situations is the case, then report that instead. So natural first step is to compute shortest distances. So let's run Dijkstra's single source shortest path algorithm from vertex 1 to find the shortest or the least amount of time to get to any other vertex. From here on out, when I say the distance to some vertex, I mean the distance from vertex 1 to that vertex. Now, another pretty natural follow-up question is when can an edge be on a shortest path leaving vertex 1? Well, such an edge can only be on some shortest path if taking it kind of satisfies the shortest distances to both vertices on the endpoints. One way to kind of convince yourself of this is if you traverse this edge and you're at a further distance when you arrive at the destination, then it's kind of impossible to make up for that time. Otherwise, you would have a shorter path. Okay, so given this, we can filter out our edges and only include edges that appear on some shortest path. However, this isn't quite sufficient because we don't just know that Bob took a shortest path. We also have all of the travel log information to deal with. So how can we incorporate that? Let's go back to our example and think about it. So what if I told you that 3 is an entry in Bob's travel log? Is that sufficient to determine which path he took? It's pretty intuitive that Bob has to take the top path. He has to go to vertex 2. He can't go to vertex 4. One way of thinking about this is if Bob takes the bottom path, if he takes the edge of weight 5 from 1 to 4, then he kind of skips over a city at distance 3 that really should be there. Generalizing this a little bit further, an edge is valid if it can be in a shortest path using the property we talked about, and there's no entries in the travel log that kind of contradict this edge. There's no entries in the travel log that say there should be a city in the middle of this path. Note that the interval written on the slides is exclusive on both ends, because at the endpoints of those distances, there are cities there. That's where city U and city V are. So it's fine if those specific values are in the travel log. Okay, so given all this information, we've filtered out the edges to ones that are consistent with our shortest path criteria and consistent with our travel log. And once we do that, the remaining edges actually form a DAG. It's impossible to go in a cycle, or otherwise it's not a real shortest path. And now that we have a DAG, counting the number of paths from vertex 1 to any other vertex is a pretty classical dynamic programming problem, and you can solve this in linear time. Going through this really quickly, the method is to topologically sort the DAG. In our case, we get this for free because we already know the distance to every other vertex, and those two are pretty much the same thing. And then we can keep track of how many paths there are from vertex 1 to the other vertices, and if we process the edges in order of distance to the source vertex of the edge, then we can kind of push this information through. And this is pretty much all you need to solve the problem. So find the shortest paths, find all of the shortest paths, figure out which edges are valid, and then run this dynamic programming to count the number of edges, or count the number of paths. Then if there's exactly one path from 1 to n, just walk backwards and output that path. There are a couple of implementation details we should go over though. So the first one is I kind of glossed over how to check if the travelogue is consistent with an edge or not. You can't actually step through every entry in the travelogue for every edge. The number of edges times the number of entries in the travelogue is just too large. So there's two ways to go through this. Both involve sorting the travelogue. One way is to binary search the travelogue to see if there's an entry that contradicts the edge. The other way is, as you're running the dynamic programming solution, to step through the travelogue and see if that contradicts the edge you're looking at. The binary search is slightly slower, but it's not enough to matter for this problem. The other thing to note is the dynamic programming formulation I mentioned in the prior slide counts the number of pads, but we don't actually need all of that information. And it's actually pretty hard to keep track of that information. The number of pads can be exponential. So we only care if the number of pads is 0, 1, or more than 1. A couple of different ways to implement this. The easiest, I think, is to just store 0, 1, or 2 in your table. And if any value ever goes greater than 2, kind of clamp it back down to 2. If you try and use overflow, if you just let your integers overflow, you could get some incorrect values for the number of pads to vertex n. Using a random modulus is probably safe, but why risk it? Practice safe programming. The final kind of gotcha in this problem is if the travelogue has any distances in it that are beyond the last vertex, then something has gone wrong and there's no valid paths, because there is no shortest path from vertex 1 to vertex n that then visits further vertices. And that's about it for travelogue. So like I said earlier, you run Dijkstra's algorithm. That's m log n if implemented with binary heaps. Then d log d to sort the travelogue, and then a linear time algorithm to actually compute the number of pads, and then maybe another linear time to reconstruct the path. If you binary search, maybe an extra log factor. I hope you enjoyed solving this problem.